Now that you've had some time to play around with other models and trying out different variables and different combinations, if you have found a better model that works better than Model 3 and satisfies all of the assumptions that we have tested, you can move forward with that, or we can work forward with Model 3. So let's just take a quick review of Model 3. And Model 3 included the median household age and the number of bedrooms. Its R squared was 0.048. So let's check the multicollinearity of the model. We are using the value of 4 for VIF, and if it's above 4, we want to think about issues of multicollinearity. In this case, the values are very close to 1.25. Nothing we need to worry about there. Now, we need to test if our residuals and our independent variables are correlated. And we can use the core.test. So here we look at our p-value, and that's at 1. So now we know we cannot reject the null hypothesis. And if we look at our correlation, it is pretty much nearing 0 for the median age. And this number of bedrooms, again, neither of these are significant. So we are just going to move on, and we can say that no, there's not correlation between our residuals and the independent variables. We want to make sure that our residuals are normally distributed. This assumption, as we discussed in lecture, can be somewhat relaxed, and we can just check it with a histogram, and we see that for the most part it's pretty normally distributed. If we were to be more exact and use our Shapiro test of our model residuals, we will find that no, they are not normally distributed, and that we would reject the null hypothesis that it is normally distributed. Now, what is probably going on here that we haven't tested yet, and we'll move on from this anyway, is that we know we have spatial data, and we haven't accounted for any issues of spatial autocorrelation just yet. So let's move forward to look at spatial autocorrelation, or generally autocorrelation, our data. So as a review, we cannot to satisfy the assumptions in our linear regression model, our residuals cannot be temporally autocorrelated, that meaning the based on a time series, the residuals for, say, t time 10 cannot be correlated with time 9, for example. Or in space, we need to see if neighboring values or near values are correlated with each other for the residuals. However, right now, we don't have spatial data. We have a tibble that just has each of our observations as a row and each of our variables as a column. So we will need to import those spatial boundaries, join our tibble to that data, and then join the residuals from our model to those spatial polygons as well. We're going to use Moran's I to calculate the global spatial autocorrelation statistic. And then we will walk through if spatial autocorrelation exists, fitting the spatial lag and the spatial error model. Now, these models are much more difficult to interpret than the linear regression model. And in this course, we're not getting into too much detail about how we interpret them. We have discussed some of the theory about the differences between the two models and why you may choose one model or the other. In our tutorial here, we will just go through the process of model fitting. Now, spatial data in R. At the time of writing, many people are still working with the SP package, but the SF package, or simple features representation of spatial data, is gaining in popularity. So that might be something you think about in the future. But we will work with the SP package and its data constructs that it has for spatial data. We have three common uses. We have spatial points, spatial lines, and spatial polygons. These are three classes of data that allow us to store geometry. We also have, for example, with our spatial points, we have an extension of that called our spatial points data frame. And that allows us to store variables along with the geometry. Now that's what we are interested in. And we're actually going to be working with polygons. So let's load the SP package. Let's call up the help for our spatial polygons data frame. And it's telling us it's used to create objects of class spatial polygons or spatial polygons data frame. Now, we have our data. We know that our polygon data is stored on that GitHub account. Okay. So how do we read in spatial data? Well, we have a library or binding in R called the rgdal library. And that allows us to use the commands in GDAL. If you're not familiar with GDAL, just do a quick search on the internet and learn about that library of functions for reading and writing spatial data. That's used across many different spatial packages, different programs. But let's just load that library up. Here it's giving me some information, some feedback. It's just saying that I'm working with GDAL version 2.1.2. Yours probably different than mine depending on when you're working on this. And the function that I'm interested in is the read OGR. Okay, we can read a bit about the OGR function. I'll let you do that here. Now, we know we have lots of different ways of saving data in spatial coordinates. We have our shape files that are very common when we're working with ArcGIS, but we also have different ways of storing our data. And in this scenario, we will be working with a GeoJSON. But what we can do, there's this function called OGR drivers, and it's going to show us all of the different types of data that we can use or we can read in that are spatial data. We have our Esri shapefile here. We have our GeoJSON. We have map info files. We have the file geodatabase from Esri. We have XML files from OpenStreetMap. We have PCI, DSK files if we're using PCI software. You can see that there are many different drivers, so we can read in lots of different data which is great using this rgdal package and the read OGR function. The read OGR function works just like our other read functions. We can direct it to a file on our hard disk, or we can point it somewhere on the internet. So let's read in our polygons, and this is a GeoJSON. If you're interested in that, you can look into more detail about that on the web. And we will just call it California_polygons. This will take a moment to read in. All right, it's still working away here, but it's going to give us some information about which driver it used, because we didn't specify it. We could have specified it, but it was able to figure it out on its own. So it used the GeoJSON. Shows us our source, the layer, how many features, and that it has one field. We can use the class function to check the class of our object. And we can see that California polygons is stored as a spatial polygons data frame. And that class is defined in the SP library or package. So let's just do a quick plot to see what this looks like. So we can just call plot on our spatial polygons data frame. It's going to take a moment here as it's reading the geometries and creating our plot. And we see that we have all of the census tracts for California. We can also look at different parts of this class using the @ symbol to access different parts of the data. And so here we can access the data frame using @data. And we see our data frame is the GeoIDs. And that is what we can use to join our data. So before we join our data, let's create a new data frame. And that data frame will have the model residuals and the model input data stored together. So we can use the column bind function, cbind, which is going to combine columns, variables, and we're going to create a new data frame. So let's just see what that looks like. So here's our new data frame. We have our GeoID, we have all the input variables that we had available to us, our independent variables, and then we have a row of residuals. So we can join our new data frame to the SP object using a function in the SP package called merge. So we're going to merge California polygons with our new data frame that we created. We're going to use the GeoID. And then we want this all X allows us to decide, do we want to retain rows in our X, which is our California polygon, when they have missing data or data doesn't exist in the data frame. And in this scenario, we only want to retain the polygons that we have data for. And we'll create this as California underscore SPDF. So now we have our new object. And if we want to look, we can look at its class. The spatial polygons data frame. We can look at the data itself, that data frame. And we use the @ operator. And we can look at the data, polygons, the bounding box, the projection. Let's just look at what a projection string looks like. So here, it's telling us it's in lat long. The data is WGS84, and that we're using the WGS84 ellipsoid. We'll deal more with that in the future. And we can look at our data here. So here's our data attached to our California spatial polygons data frame. Now, we can map our residuals using the spplot function. So this allows us to plot an SP object. Okay. And here we go. And we have San Diego here, and this is our residuals. And it's a pretty odd color scheme. Now, in our cartography course, if you took that, we learned about color brewer, and that we had different color schemes that were suitable for maps. Well, in the R world, we also have access to this. And so we have a function in the R color brewer package. Let's load this lattice extra package. I forgot to load that. And it's going to load lattice in our color brewer, which allows us to do some improved plotting. And here now when we run the function, we can see these different color schemes, and they are identified by these IDs here. So for example, this is yellow, orange, red, or red to purple, or just reds. So to use these, to make our map much nicer, we create a color palette. And so we use the function brewer.pal, and we tell it the number of colors we need. And this is going to be based on the number of breaks. And we're going to use the BRBG. If you look at that here, that's this color scheme. And we can view the color palette, and it's going to give you the color ID numbers. Okay. That's how R is storing the colors. And here we can generate our new map. And so we'll use that same California spatial polygons data frame. We'll tell it how to color our regions using our color palette. We tell it how many cuts to make. Okay, and this needs to be -1 from the number of colors in our palette. And then here in this scenario, we will just make our borders of the polygons transparent. So let's take a moment to plot. There we are. We have a much nicer looking map. Now, one thing that I do notice for our residuals, that our high residuals seem kind of spatially correlated in here. Low residuals seem kind of spatially correlated out here. We will end this video here, and in the next one, we will look at how we calculate out the Moran's eye statistic for spatial auto